G'day everybody. Welcome to the presentation. I'm David Lee, and this meeting is hosted by UniSC and the IFO Division 5.01, looking at resistance drilling of standing trees for wood quality survey. And this is a Resi Users Group meeting. What we've been sort of running these meetings, I guess, over about 4 or 5 years. We've had a bit of a hiatus for the last couple of years, where we've had a fairly large research project ongoing, and we're sort of just trying to reinvigorate the Resi Users Group, because it's the group of people who are using Resi to look at wood quality is expanding. Now, what we've got is, with this, we've got 3 presentations today. Hopefully you can see this first slide. I'm just trying to get it to move on, and my computer's going very slow. Okay. Well, for some reason it's dropped out of presentation mode, but we've got a talk by Brian Rawley from YT Gen about how Resi data has been incorporated into YT Gen and how it can be used to output wood quality and yield data. And then we'll have a talk by Villas, sources of measurement error and resistance drilling, and then Rebecca Cherry from Hine. And I see that all 3 of them are online at the moment. Uses and benefits of Resi data for Hine. And with this, I guess one thing that we're looking at is, we've got the 3 presentations, but we want to encourage people to give presentations also. This isn't about the researchers talking to the industry. This is about industry and people who are using the Resi actively, looking at their issues, their problems, their benefits, and how they find for Resi. One thing I just ask everybody, can they go put themselves on mute during the presentations, so we don't get any feedback? I can hear somebody typing away at the moment. And so without further ado, I'll ask Brian to start his presentation. So over to you, Brian.
Okay, thank you.
Just before we go one step, if you've got questions during the presentation, perhaps you could just put them into the chat box. And then if we've got questions, at the end of each talk, they can be directed directly at Brian, or I can read them out, or you can read them out from the chat box. Thanks very much.
Thank you, David. Hello, everybody. My role in the project has been largely one of turning all the good science into something that's hopefully useful to wood supply planners, including people like me. And today I'm going to talk about how basic density models have been incorporated into YTGen and how these can be used to add basic density information to yield tables used for wood supply planning. For those who aren't familiar with YTGen, YTGen's software that helps users develop yield tables, and it does that by simulating tree growth and log making, basically. It's got a bunch of other stuff like thinning and things like that, but the key thing is it predicts volumes of log products by age in the future from inventory data. It provides a framework for incorporating biometric models from multiple sources, and it's got growth models from a lot of people, and now it's got basic density models from a variety of people as well. It's supported bespoke basic density and acoustic wave velocity models since 2008, but the models in there are currently New Zealand ones. And so I modified it as part of this project to support basic density models developed from this project, and also to allow users to configure those models by adding model coefficients to support new models as they're developed. It supports 3 basic density models. Or put another way, the basic density, the key aim is to attach basic density information to predictions of log volumes in the future from Resi traces that were collected with inventory at mid-rotation. And to do that, the model's been split 3 ways. And partly that's to make it more flexible for people to modify, but partly because that's sort of naturally how things work. The first model is imputing breast height disk density for trees where breast height disk density was not measured. And I'm assuming for most people, this is optional, but I'm assuming for most people, you're not going to put Resi trace from every tree in an inventory. So for the trees where you haven't done it, you're going to want to impute density from the other information. Second part of the model is growing breast height disk density from age of measurement to age of harvest. And the third part is predicting disk density at any point on the stem from breast height disk density. And if you put all those bits together, then you can predict density for estimates of log products in the future from data collected at mid-rotation. Now, I should point out here that YTGen doesn't know or care about Resi as far as it's concerned. It's dealing with basic density. It just happens that Resi is a convenient way of collecting the data at mid-rotation. It's also quite a good way of collecting data for building the models. So all of the models I'll talk about were built using data collected from Resi traces. So predicting breast height disk density at time of measurement is a simple model. It's basically a 2-part distribution model where the distribution of disk densities is divided between plots and trees in total. So there's an assumption that there's a between plot variation and a between tree within plot variation. And specifying that to YTGen involves adding information to the stem data collected during inventory using a user variable. In this case, breast height disk density was 400. Adding a stratum average if not all of the trees have their own breast height disk density. And if the tree level breast height disk density is calculated as provided, it's going to be used. Otherwise, it's calculated from the stratum average using coefficients that are provided by the user in a method file. And those coefficients are basically the between plot standard deviation of the log normal distribution and the between tree standard deviation of the log normal distribution. In a yield request, I'll come to this later, I'll give you a demo, but for people who are used to using YTGen, in a yield request, the model is specified using another user variable, which gives the identifier for the model from the method file. So second part of the model is growing that breast height disk density from age of measurement to age of maturity. That's an example of a model based on data collected in permanent sample plots in South Australia and kindly provided by 141. Don't worry about this is actual data, and so we've got a bunch of suppressed trees that basically stopped growing at age 20, and so their breast height disk density didn't go up. But for a normal tree, which includes most trees, like suppressed trees are stocking sort of up on 2,000 stems per hectare at age 20, which is not really normal for radiata in South Australia. For other trees, the growth follows an asymptotic yield curve. In this case, a monomolecular curve with the asymptote predicted for the individual tree. Then, in specifying that in YTGen, so growth is for a single tree and it updates breast height disk density. The coefficients are provided in a method file. And in the yield request, the name of the family of growth curves is provided using a user variable. The final part of the model is density at any point on the stem predicted from breast height disk density. That's an example of a model from a paper study kindly provided by Forestry Corporation, New South Wales, where, can you see that? Along the x-axis, you've got the top of the tree at the left-hand side, the bottom of the tree at the right-hand side, breast height where the vertical line is. And you can see that disk density decreases as you go from the bottom of the tree to the top of the tree. And the slope of the increase is a function of the breast height disk density, so that trees tend to end up at the very top, not going down to a minimum. And specifying that in YTGen, so the coefficients for the relationship between breast height disk density, relative height and disk density are again provided in the method file. And in the yield request, that those coefficients are specified using user variable. And within YTGen, when a log is made, the log density is calculated as the weighted average. That's by diameter inside bark squared, the weighted average of disk densities along the log. I did this slightly because I wasn't sure that people actually understood why I was doing this, or why it would interest them. Possible uses, and I've, as a forest planner in a previous life, have used all of these. Avoiding surprises in wood supply, smoothing the properties of wood supply. So both of those go hand in hand. Like, that's making sure that your basic density doesn't go up and down simply because you haven't thought about it. Investigating the consequences of management allocations decisions. Two of the things that you can play with when you're allocating wood to a mill are basically how far up the tree do I go and how old do I cut my logs. And both of those have an effect on the density of the supply. You can use it for planning processing that best utilizes supply. Like, there's no point building a mill that's optimized for wood properties that you don't have. And if you're interested in pulp mills, you can use it to predict supplies, total fibre in oven dry tonnes per hectare or oven dry tonnes per year. So for people who are currently using YTGen and want to incorporate those models, the steps are: install the latest version, or version greater than 3.16. Add the model coefficients to YTGen method file. I've got method files for all of the models I've developed as part of this project. I'm happy to send those around. Add stand, mean, or single tree breast height disk density to population files. Select the coefficients in a yield request. Invoke the density model using a global model invoker, and output is available in the standard output as oven dry mass, kilograms per hectare by grade. The reason for using oven dry mass is that it's additive. Like, you can't lose fibre if you deal in oven dry mass, but it's easy enough to calculate. Density is basically oven dry mass divided by volume. So I'll give you an example, going through those steps. Here's a simple 2-tree inventory file, and you can see that I have population, stratum, plot, tree. On my stratum, I've got a stratum average breast height disk density, which is notionally collected using Resi data and averaged. I have, for this tree, I have got its own breast height disk density, and here's a tree without it. That tree will have one calculated from the average. Now, obviously, in in an inventory file, you're going to have a lot more trees than that. Like, here is a bigger example with many more trees, but it's easier to see with a small sample. If you look on the method file that I'm using, I have a number of coefficient sets. I've got a density distribution model from this one's based on radiata inventory in South Australia, and again kindly provided by OFO. My between plot standard deviation is 0.044, and my between tree is 0.063. That's between tree within plot. I have a density growth model, which has a which has coefficients. And I've got two within tree disc density, one from Forest Corporation New South Wales paper study and one from Timberland specific study. I also have a breakage function and a taper function. Now, I need a cutting strategy, but the cutting strategy in this case doesn't vary from a standard YTGen cutting strategy. It doesn't take into account density as it's cutting the logs. So I've only added two logs, very simple ones, a saw log and a pulp log. But I want to know, after I've cut the logs, how the saw logs are distributed by SED and basic density class. So I have got a set of grade recovery rules that divide my saw log into 10 centimetre SED classes, and then divide the saw logs into 50 kilogram per cubic metre basic density classes. If I put all that together, I have a yield request that uses that cutting strategy and those grade recovery rules. And sorry, last thing I should have shown you was I have a set of rules that say assign basic density models I'm using. This between tree density variation model, this growth model, and that within stem, this density, so that variation up the stem. And from other stuff, I'm using that taper function and that growth model and that breakage function. So when I specify that as a yield request, so there's my cutting strategy and my grade recovery rules and my rules which models I'm using. And I'm going to grow my big sample of trees from to ages 20 to 40 by 1. And I'm also going to thin it down to 400 because it actually starts out at age 10 with about 1,500 trees per hectare, which leads to uninteresting results if you grow it. So what you're doing is actually growing those trees, cutting them up into logs, adding the basic density and sticking the results in a database. And I can suck them out of the database using a spreadsheet that basically queries the database and populates fields in the spreadsheet. And you can see that this is our stand summary, so it's one number per age. I have got my thinning results at age 10. Then I've got results at clearfill at age 20 to 40. And I think the interesting things here, the total recoverable volume, the up and dry mass, and a calculated basic density from oven dry mass divided by total recoverable volume. I've also got at each age, I have estimates of pulp volume and saw log by SED class and basic density class. So in this one, so if we take saw log, 20 centimetre saw logs at age 20 with a 300 minimum basic density, they have a very small volume. They have an oven dry mass of 26 kilos per hectare, and can't actually see the right hand side of the screen because my participants are hiding it. Hang on. There we go. 349 cubic meters, kilograms per cubic meter. When we get up to age, age 40, I have 60 centimetre saw logs with a minimum basic density of 500 and an average basic density of 522. Now, I'm not very familiar with graphing from Excel, so I prefer to do this using R. So this R script is querying the database and generating some graphs that I can look at. So age years, my log grade basic density, and I've summed these by SED class. So my pulp log average basic density is going up over time, and the same for my 20 centimetre saw logs, 30 centimetre saw logs. What you'll notice is that the basic density goes up and down, which is this kind of trade-off between age and where in the tree you go. As as your age increases, what happens is your 20 centimetre saw logs simply move further up the tree, so their basic density doesn't actually change very much. And the big driver of pulp is actually the waste bits that are left behind between the other grades. So we have recoverable basic density by age. We've got our volume by SED classes. And you can see that our saw log 20s, basically, our saw log 30s goes up with age and then goes down again, which is typical. As you hit a particular age, you get enough trees big enough to produce it. And then as the trees get bigger, the proportion, the volume goes down because you're simply moving up the tree. And then the oven dry mass by grade. So that's it from me. And if there are questions, I'm happy to take them.
Brian, Jan here.
G'day, Jan.
Great stuff, I reckon. Just you're given an example of a simple cutting strategy.
Yep.
Is my assumption correct that you could have a more complicated one where you, for example, would, for the same saw log size and length, you could apply different prices for depending on density, and can you make it part of your definition of a product?
No. The limitation is it won't calculate the basic density until after the log is made. So you can't have basic density stuff in the cutting strategy. You can use the breast height disc density in the cutting strategy, but you can't use the log density. And there's sort of an efficiency reason for doing it that way, is that if it has to calculate the basic density of logs as it's making them, it slows things down enormously. So typically what you do is cut and then grade afterwards. Okay. I think, Jan, too, part of the sort of the practical interpretation of that limitation is that in general, when you're making logs in the bush, you don't know what the density of the log or the acoustic velocity of the log until after you make the log. You might know something about the tree, but you tend not to know about the log. And so that in a practical situation, you don't have that information to optimize.
But you could, I guess, as a desktop exercise, try to work out what kind of a distribution of lengths, or what your well, maybe you make your first log a bit shorter than your second one, and depending on what you actually what the density distribution is within your logs. And just thinking that potentially there is some optimization or something you could learn from doing that.
Yes, you can. To answer your original question, you can make the cutting strategy as complicated as you like. But having the basic density model in there doesn't change the basic structure of a cutting strategy, so you can make it really complicated. If you're just doing a desktop exercise, what I've done in the past is I've pre-calculated zones of basic density within the individual trees by applying a simple cutting strategy, and then I've used the information about those zones to inform a complicated cutting strategy. It's not something I'll do in a production sense if I was generating, a complete forest description or for wood flow planning, but it's useful as an exercise for working out what might happen.
Thanks, Brian.
Have we got any other questions for Brian? I guess I had one. Sorry?
Yeah, sorry.
It's Charlie?
David, I put one in the chat. So how do you account for a late thinning? Because in Africa, we rarely do things on time, and late thinning changes density and volume.
I've actually included thinning in this one. and I've said thin straight away. But if I said thin at age 20, down to 400, and like in New Zealand, like South Africa, historically people have really thinned on time as well. I have an aversion to thinning because on paper it always looks good, but in practice it's never as good as you hope it's going to be.
Yeah, it's actually the ability to simulate the effect of late thinning is a really good way to persuade management to come up with the cash.
I totally agree with that. Yep.
Right, thanks.
Yeah, so I basically just changed the age of thinning and potentially changed the post-thin stocking as a consequence of changing the age, and the results change.
But one final, or maybe one quick comment or question, please, Brian, from Wolfgang. Yep.
G'day, Wolfgang.
G'day. The basic density model that you've got, does that work backwards like some of the other models do? And if so, how far can the age go back, do you think, with any reliability at all?
It depends on how you parameterize the basic density model. So
if you're producing a yield table that starts at age 5,
yeah,
which of course we do, so at what point, like, can you get your density data or your measurements or your estimation or whatever it is back to about that age, or 8 or 10, or when is it, do you think?
pretty sure you can go backwards. There's no fundamental limitation in the basic density model that will prevent you going backwards. So the answer is actually going to be any good, which is a function of how good your growth model is at going backwards and how good that density model is. But if you're, for example, starting at age 5, you're probably not measuring the breast height disc density at age 5 because it's all corewood. So, you know, my gut feeling is you don't want to stick a resi into a tree for doing this sort of stuff much before about age 15. But you could...
Well, routine inventory for us will start probably around 9, something like that. So do you think that's too early?
Pass. The experts would know more. Experts on these things would know more. My gut feeling is it probably is.
Well, I suppose we'll have the data to test it anyway. So yeah. Okay.
In the New Zealand models, and I'm not sure if I've actually incorporated this with these ones, is that I was able to specify the age at which the breast height disc density was collected, and then I could superimpose data from older measurements onto younger trees. And it would take account of the difference between the measurement age and the measurement age of the density. I need to check whether I've done that this time, but it would be a useful thing to do.
Okay, thanks, Brian.
Dom or Jeff, do you have a comment in response to that age on when you drill trees?
Yeah, I would have thought, maybe 10 to 12 would have been okay, but we want to be talking about whether we're dealing with accuracy or precision here as well. So it's probably something we'd be worth having a bit of a chat about at some stage.
So
Originally
in our experience, half rotation, which is close to 9-10, is perfect. But we're only growing to age 20.
Thanks, Charlie. I know that when Dom was looking at the genetics and using the Resi was not great at predicting the wood quality of the material now, but it was better at looking at what it would be at harvest age than the ST300, I think, at age 10. Is that correct summation of what we've found, Dom?
It was fairly similar to the ST300. Yeah, that's right. Yeah. So, and I think that's probably driven by the genetic correlation, the age genetic correlation in density, which tends to be very strong. And density being more important in the older trees than it is in the younger trees, but the age correlation being strong. Yeah.
Yep. Duncan's dropped a comment into the comments box. What is the risk of using OFO density growth models on other estates?
That's a fair enough question, Duncan. Actually, I'm going to go back to, for answer that, I'm going to go back to Wolfgang's question. That Forestry Corporation New South Wales data went back to age 10, and it looked pretty good to me. Now, Duncan, yeah, there's always a risk in using other people's models, and you're better off to develop your own, which is why I made it parameterizable in YTGen so that you can develop your own. And if you look at the reports that I wrote for the project, the sort of the basics of the method for developing your own models is built in there.
Okay, that was probably the question, Brian. If we chose to develop our own, the methodology is well enough defined that we could go and parameterize that model with our own data.
Yeah, you could, or I could do it for you, or you could do it yourself. My intention in making it parameterizable was that people would do their own models.
Sandra, you got a comment? I guess one thing, Brian, how would you use the data that comes out of YTGen to put in data into Woodstock, which is separate from what your YT10 Gen data? But I was just wondering, is it directly applicable? I understood that there was an ability to do that.
Yeah, there's a question of scale, right? Because if you're using Woodstock, it means you've got a big forest, which means that you've got lots of yield tables. And so in a typical, I only showed you one yield table there, but typically when I'm working with a large forest, it will be thousands, if not tens of thousands of yield tables. So, but YTGen is designed for batch processing that sort of stuff and calculating it, putting it in a database from which you can extract Woodstock input file, which is basically the process that people use. And then in terms of basic density within Woodstock, you can set constraints. Let's say, for example, you want a particular steady state in both oven dry mass and volume, which will give you a steady state and density. So that sort of thing has been done before.
Are there any more questions for Brian? Otherwise, we'll thank him and
just a brief comment about how valuable. I just think this work is so valuable in that it's given growers who are using YTGen the capability to manage not just wood quantity but wood quality as well into the future, and hugely valuable. And I'm curious, Brian, about the prospects for extending this work from what's currently modelling density to modelling MOE.
Provided the data that's there to produce the models, then it can be done. Like YTGen already supports acoustic velocity rather than oven dry, rather than MOE. I actually prefer acoustic velocity or propagation time simply because it has nice properties in terms of adding it and averaging it and things like that. Whereas MOE is one of these things which is only very well defined for a particular part in a particular process, and it has many definitions. So So Wattingen will already support the acoustic velocity. It could support MOE if somebody would come up with a decent definition and come up with a way of producing the data that enabled similar models to be produced.
Great, thanks.
Well, thanks very much, Brian, for that interesting presentation. And I'm sure everybody here has really got a lot out of it. We'll now move on to Willis, sources of measurement error with resistance drilling. And Willis, can you start your presentation, please?
Yeah. Hi everyone. I'm wondering if you can hear me well.
Good. And this presentation is up.
Okay. Yes, I'm just going to present the sources of measurement error with the resistance drilling. So we took like several works, like to see how much is the error is contributed to the drilling resistance, and like me, David Lee, Dominic Kane, Shannon Kumar, Jeff Downs, Marco Lausberg, and Jonathan Harrington we work together. So the drilling resistance technique is a routine method among Australian forest growers for standing tree assessment, and is relatively cheap. It is easy and is sufficiently precise for the commercial use. And that's especially when it's facilitated by the web-based trace processing platforms. So using the Jeff's website. And it is low cost in field application, and then you get relatively high resolution data from these measurements. So how does it work? So the Resi works by like drilling the needle in the tree with fixed rotation and fixed forward speed using the 3 millimeter diameter needle. And when the needle goes in the tree, it measures the amplitude from 0 to 100% at 0.1 millimeter intervals. And it measures both parameters, drilling resistance and the feed resistance as well. And here you can see the typical trace produced by the Resi. And here you can see the friction effect as the needle goes in the tree. It's accumulated by the wood chips and it's increasing, but that can be reduced using the friction correction in here. So the measurement error, so we assess how the feed speed and the RPM affects the drilling resistance. So the instrument and operator influence, the Resi needle wear to see how long you can use it using a single needle, and then how the Resi needle diameter itself has an effect on amplitude, and using different batteries. So the feed speed, it affects the amplitude. So if you're using the low RPMs and then the high feed speed, so you're getting very large amplitude, and that is done because of the chip thickness. So as the needle goes in, so it cuts the chips. So yeah, this part spins all around 180 degrees and then cuts a wood chip. And then these parameters, the RPM and feed speed, affects how thick the chip is going to be cut. And then the chip thickness, if this chip thickness is high, so the amplitude it becomes much higher. And then the correct word that would be the feed rate per major cutting edge. So would be feed rate per that part of cutting. And the bigger chips requires more force, so resulting in the higher amplitude. And then how the chip thickness affects the amplitude. So like the big chip thickness, so it produced this kind of very wide amplitude graphs, while the small chip thickness, it produced like low Resi amplitude, but it's kind of like very flat. And big chipness could result in the instrument overload. And then while small chip thickness it might not capture the all data. And this shows how much, so this is the maximum possible like settings using the drilling resistance IML instrument. So 200 centimeters and 1,500 RPMs, and this is the minimum possible. So ideal is to use the largest possible chips to get the data, but because due to overload, so you need to use something in the middle. So this in the middle, it shows the optimal sampling conditions for the softwoods is 200 and 3,005 RPM, and then for hardwoods, for that would be for plantation and pulp grown hardwoods would be 100 centimeters per minute and 3,500 RPM. So sometimes it's not possible to keep the same settings, and then so you need to change the RPM and feed speed, and then to combine this into a single effect, you can use the chip size. But that also depends on the species. So you can see for higher density hardwoods, so the chip size is different than for the lower density wood species. And then using these settings, like this function, so you can adjust for any particular feed speed and RPM for the particular species. So the next study we did, we tested the instrument and operator influence. So we tested Southern Pine, we tested six sites and 30 trees per site, 2 operators, 7 Resi instruments, and then we compared two types of instrument, PD 400 and PD 500. So we used fixed feed speed and RPM and used the same diameter needle. So here the results, you can see the amplitude.
Just trying to do 3 things at once, actually.
Yeah, so there was like no effect on operator, so there was like no effect. And then also different Resi types, PD 400 and PD 500, so they also no effect. So when comparing different type of instruments, so you can see there was a statistically significant difference, but practically it was only 1.7% difference between the instruments. So you can see the instrument 1 and 2, they were kind of older instruments, so they were they generated slightly lower amplitudes, but most of the instruments, they were the same. And then how much it would change in basic density for each instrument. So you can see one instrument, it under predicted basic density by 9 kilograms per cubic meter, and the other instruments would over predict by 5 kilograms. So like if companies using like multiple instrument, and then you need this precision, so you could calibrate on for example on several boards, and then subtract these values to avoid this error. And then, so in summary of this particular study, so one Resi instrument predicted this basic density under predicted basic density by 9 kilograms per cubic meter, other over predicted by 5 kilograms. So the operator had no effect on basic density prediction, and 2 types of instruments, they gave the same result. So the other study was to see how much I can use the single Resi needle up till the result becomes different. So we tested on 25 years old Southern Pine logs, so they were fresh, and which were approximately 500 kilograms per cubic meter. And then we tested using the feed speed 200 and 3,000 RPM, which is considered standard for softwoods, and we drilled 400 times 4,000 times in the tree just to worn out the needle, and each drill length was set to 150 millimeters. And the same thing we did with different alternative feed speed and RPM settings. So the needle were tested each time, so like multiple stages, but you know the needle would be 400 millimeter long or 400 millimeter long. So we had to find a way how to test without destructing the needle, and we use just a simple microscope. And then this is what's happened when we were drilling southern pine with 200 centimeter per minute settings and 3,500 RPM. So you can see that the needle were starting to appear in the edge of the corner, but you see it was very minimal. And that's after the 600 meter. And while using different settings, you can see the needle wear become much more expressed, as you can see in here. So here is the result. So the total drill length in meters, and then drilling resistance amplitude. And then here is the rotational drilling length, because you know each setting, it gives different rotational length because it spins much more and then it goes much slower. So it, in this case, would be 10 kilometers, and here would be almost like 30 kilometers. So you can see for the 600 of total length of using the resin needle, there was no effect in the drilling the southern pine. But when using different setting, which is more aggressive and spinning much more faster, so it was possible to drill like 300 meters without being affected. And then afterwards, it was kind of the amplitude started slightly to increase. So here you can see, you know, there was no effect. Even that wearing is not going to do any changes, even this one. But from here, so it's becoming too much of one, and then the effect is going to be significantly different. So to summarize, so there was no effect up to drilling resistant amplitude up to 600 meters of drilling. So with the standard setting of 200 centimeters per minute and 3,500 RPM. And the amplitude was not affected up to 300s using the alternative setting 105,000 RPM. But at the standard setting, so that would result in 857 meters like of drilling, and that would result in approximately like 3,000 trees of 30 centimeter diameter. So you can drill safely using the single needle. But it's worth to observe the needle, like if you hit the knot, or also when changing the resin needle, is worth considering when you're changing with pliers to make sure the needle doesn't spin through pliers. Because one time for me it happened, it spin through, and then the damage is quite great. So it's better to change the new needle and don't use that one. So the other study what we did, so we compared different resin needle diameters. So you can see we got diameters ranging from 3.08 millimeter to 3.30 millimeters. And then in general, for the forest assessment, we're getting these needles. So this needle we wouldn't get because the IML, they class as a forestry grade needles. And mostly there was no significant difference between 3.11 to 320, except for one needle. And we don't know why this needle, it was different. As we assessed using microscope, it looks identical like the rest needle. And in total, the maximum difference between the 12 needles, including non-forestry grade needles, there was 2.3%. But you know what we typically get for the forest, so that would be difference 1.7% difference of the amplitude effect using different diameter needles. So we tested, for the next study, we tested the battery effect. So we got range of batteries, and then we tested on the logs. And here we can see the the different batteries. So there was like old batteries versus new batteries and different amperage of batteries. And then you can see the effect was very minimal. So it's only this needle was slightly higher than this one. And that in total, it was a result 0.5% difference due to battery. So yeah, statistically significant, but practically is very small difference. And in summary, so the chip thickness allows to account for different sampling conditions using different feed speed and RPM. So operator has no effect. Instrument types also no effect, whether you're using PD 400 or 500. But the instrument variance resulted in maximum possible difference due to instrument was 1.7% or -9 to +5 kilograms in cubic meters. And the Resi needle wear, so it was safe to drill 2,857 softwood trees using of the 30 centimeter diameter trees. And but that would be for softwood. So for hardwoods would be different result. And the Resi needle diameter from 3.11 to 3.20, there was no difference, but only one needle gave the different result, and that the difference was 1.7%. Then the Resi battery maximum effect was 0.5% of difference. And then, yeah, we would like to acknowledge the project partners, and yeah, I'm happy to answer any questions.
Thanks, Phyllis, for that presentation. Has anybody got any questions for Phyllis?
Yeah, Kelsey Joyce from Foraco here. Is there any intention on doing the needle wear work again, but with hardwoods?
Yeah, I did a little bit on Corimbia. And the Corimbia was 700 or 800 cubic meters. So I couldn't
Density.
pass like density, and then maximum I could drill it was 100 meters.
Right.
So it's much more, but it was extreme. So it was, I think so that would be less than 100 meters because you need to use different settings. So you need to increase the RPM, and then when you're increasing RPM and decreasing feed speed, so you automatically even further increasing the needle wear. So you have to be careful for the hardwoods.
Yeah, I'll be keen to do it. To see it done on Nitons, which is probably between 450 and 550 kilograms.
So yeah, that would be. I'm suspecting. Yeah, would be slightly different because you're using different slower feed speed.
Yeah.
And then yeah, the wear would be higher. Yeah, definitely higher than for the softwoods.
Thank you.
Yeah, thanks.
Any other questions?
Yeah, I have one, Charlie from England.
Hi, Charlie.
So how do you know what setting would be appropriate? So we're using both hardwood and softwood and different species. How do we know when we're overloading or underloading the amplitude?
Now, usually the needle retracts. So when it goes in and instrument overloads, and when it reaches, I think so 80% of amplitude, I think is programmed in the instrument to retract the needles, so not to damage the instrument.
Okay, so
yeah, you just need to test which one is suitable, but ideal is to have the larger chip size, so it means to drill as fast as possible, which is also useful, but also have as slow as possible RPM, because in this case you can get better data than using different settings.
Yeah,
but this is like a trade-off with overload.
And then
Is there an amplitude
question,
range?
Sorry.
Yeah, the amplitude
recommend-
range. So as you're getting bigger amplitude range, you're getting better data, and it gives better correlation than using alternative settings. So if you're using the very fast RPM and slow speeds, feed speed, so that the relationship starts to decrease a little bit. You know, the relationship with basic density.
My second question is, the manufacturer recommends servicing once a year. Do you know what it is they do when they service the instrument?
Yeah, they clean the instrument from inside, and yeah, I'm not too sure what they do exactly. So maybe Jeff, maybe you could comment on that. Yeah.
What they do, Charlie, is they basically pull the whole thing apart, give it a thorough clean, get rid of any gunk and dirt and thing that's going to add resistance to the worm drives in it. And then they run it through 2 different calibration steps. So the first calibration is the standard calibration, which builds the resistance to power relationship. And then you can get an optional second calibration, which they argue returns it back to factory conditions, such that they argue every instrument should have the same relationship between resistance and power required to overcome that resistance, or amplitude.
So do you have to ask for that second calibration?
Generally, they will ask you when you send it in.
That's for the Australian supplier.
Yeah,
we send ours back to Germany.
Okay, well, then you probably want, I mean, they may do it automatically because, Germany does everything the best, but I don't know. We're probably good to check.
I will, thanks.
And also I would give some warning when testing very dense hardwoods. So it's a good idea to clean the needle, because there's some sap goes around, and then in this case I managed to damage my instrument. And also need to just look the needle wear when drilling extremely dense hardwoods.
And thanks, Phyllis. I mean, that was a really useful presentation. Gives me much more confidence in the robustness of the instrument. Well done.
Thank you.
Dean's put a question into the chat box. Are the Resi differences additive? You can't control for needle variation across batteries or instruments, for example. I guess that's asking, with all the different small variations, which each one was significant, do you think that they are, significant from when you're sampling in a forest, I guess is where Dean's probably getting at.
So if you're comparing, the difference would be 10 kilograms or 15 kilograms difference between the sites. So then this small difference wouldn't be matter. So depending, what are you testing? But if you're using like multiple instruments, so it's good to have to minimize the error.
And how would you do that?
To calibrate, like if you're operating like 5 or 6 instruments, so you drill, you drill like several boards, and then the density of this board, so you kind of get large enough sample size. So to drill at that would be quite simple, and then you adjust, which instrument under predicts, which is over predicts, and then in this case you can eliminate for the instrument related, and also it's worth measuring the Resi needle, but at the same time it's a bit hard to measure them with the calipers. But mostly IML, at least in Australia, they provide forestry quality needles, and then from the results, what we see, it was only one needle. It gave some strange result, and that difference, it was only 1.7%.
Any other questions?
Yeah, this is Xiping Wang from US. Hi, Willis.
Hi,
Very
Xiping.
good presentation. A
Thank
lot of
you.
good information. Yeah, I guess this is my first time to hear there's a forestry type needles. I don't, do they have a different needle for different applications?
Yeah, that's correct. So because like non-forestry quality, so they're measuring on the power poles, and you know that sensitivity for them is not important because they're measuring if there is like rot or not. So the small difference in percentages is not affecting. But yeah, for forestry quality, usually the needles when looking through a microscope looks that the coating looks like nice, like more nicer covered. While non-forestry quality, yeah, some needle coating was very thick. And
So
then,
typically the needles they use for power poles and things like that are a different shape and end format. With the forestry needles, what happens is that the needle diameter is fairly constant. The variance comes in when they coat them with the tungsten, and they can't control the tungsten
yeah, that's
coating.
correct,
So you do get the variance in the thickness because of that. And so what IML have done is they basically check needles for what Villas is calling forestry quality needles. That they're making sure that when they supply a batch of 10 needles, they're within a diameter range before they send them. So they manually check them from a larger batch. So someone like a routine arborist who's using a Resi for checking for decay, needle diameter isn't really an issue. It's only as we get to this more quantitative application that it becomes a concern.
Yeah.
So Xiping, you can ask IML to supply low tolerance needles or forestry quality needles, whatever. Yeah, but you could confirm with them that that's what you're getting.
Yeah, that's good information. I have never known this, so we just we ordered additional needles. And we noticed they came as two different types, and the shape is different.
Yes. Yes.
Yeah.
Yes, we've noticed that in a couple of batches too. That even with what we thought were getting the same needles, there seemed to be a bit of variance in the shape and architecture.
Yeah, I'll make sure we're using the forestry quality needles next time.
Tabanan has put a question into the chat box, which I think might be a question that probably appropriate for you, Jeff, rather than for Villas. I'm not, because it looks like it's about the website. I don't know whether you can see that. Yeah, Jeff, you still with us, or?
You're on mute, Jeff.
Yeah, I was just talking to myself, which is the first sign of madness. Second in my case. Yeah, look, I'll have to ask you to send me that particular trace and which website you were using, and I will have a look and see what the problem was.
Any more questions for Villas? Otherwise, we might thank Villas and move on to Rebecca. Rebecca, are you there? And I don't know whether you've got a presentation to give or you're just going to talk.
Yeah, I'm here. See if my video is going to work. Yep. I have got just a couple of slides to show, so for some examples of what I'm going to talk about. So
thank you.
Just go in here and share. Is that working?
Yes, thank you.
Yep, okay. All right, so I just wanted to have a quick chat about some of the stuff, so the uses and benefits for Resi data in the sawmill, which is specific really just to sawmilling, and it does depend on relationships with our log suppliers, but I'm not going to go into full detail about all the benefits to the total industry because of the Resi that look at things like keeping us competitive in the market against other products, and also getting the most out of the plantation resource that we've got with the limitations on land, available land to grow that. I think pretty much everyone should be familiar with all that stuff. So I'm going to concentrate just on the sawmill side of things once we get the information. Okay, so I just want to mention there as well, it is in conjunction, we have to work with our suppliers to get and use this information and work together to come up with solutions that will work. This, as sawmillers, we see it really as it's our responsibility for making the best decisions we can to get the most out of the available log resources. We don't want to cut a log up that's got high grade in it to sell it for a non-structural purpose. It's very wasteful, and obviously we can't get high grade material out of our low quality logs. So we need to be very careful what we do with it. And the more information we can get about our resource that's coming in now and into the future, the better. And the Resi tool provides us quite a bit of information that we can use for that. So planning is one of the major things. So not only looking at weeks, but months and years in advance. So something Brian touched on before was around the smoothing of your AWV as it comes in. So we're not getting high fluctuations. But also we can look at targeting specific like high grade compartments to get the higher grade product out that we need for our customers. For example, our glulam beam plant. So the other thing as well is the Resi data gives us information in advance where we can identify opportunities, but also challenges. So I've got examples of real data that we've got at Hine that show examples of how we could have made some different decisions or better decisions in advance if we had that information. So we do already have information from different compartments that were grown near the plantations, the compartments that are coming in now that we can make some assumptions on. But the Resi gives us a lot more detailed information that we can make, in my opinion, better decisions on if we're looking at that. Also allows us for optimizing and maximizing the value from the product, which I've already mentioned. So we could sort differently, we cut differently, and also something I'll touch on in a minute is a question that's been running around Hine for a few years, which is when is a tree actually ripe? Also, this information provides more data and incentive for further research into all sorts of areas. So, what else can we identify from the Resi data? Is there something else within a log that we can identify by comparison to different technologies such as bioluma scanners and that kind of thing? Okay, and so this is an example of real data from Hine. So if you have a look there, on that little graph on the left-hand side, we've got log AWV. So that is that line represents a month, average AWV over a month. So you can see there's a lot of fluctuation in that. We could take the opportunity to talk to our supplier if we know the product that's coming in advance in more detail, and either decide to smooth that out. So blend in some of this stuff with some of this stuff and mix it up. Which gives us a more consistent supply. Or, like I said, we could go, well, this month we're going to cut and stockpile specific high-grade products to meet our customer demand. So sawing strategy is one of the big things I think that we can benefit out of that. So if we get a log like this, so dark orange is a high GPA. This is some Resi data and results from some work we did with HQP, with Dom. And you could see that we've got this log here, which has a lot of high grade in the outer region down to, medium low, but then we've got this one here in that compartment. Very different. We would not cut them the same. And while the AWV gives us an average of our log, it doesn't give us this level of detail. So we like to know, where the boundary is of our lower quality core because we would cut that very differently. So this one here, we would run through a completely different pattern through our sawmill. So that's where we could get benefit and get more out of the log if we knew what was coming. You can see on this graph here, I'll go on to the next one actually. So it can also, we're talking about identifying opportunities and challenges. So this was the average of those first couple of years of AWV results. And you can see that our log supply dropped off in AWV quite a bit. We were not expecting that. If we could see that on the actual log that's coming in the next 5-10 years, we could make some different decisions on what we're going to do in the future and how we would plan. So, you know, do we need to consider new products? Do we need to talk about trying to get different compartments in just to top up and target saw for getting those high quality products for specific customers? So then it also allows us, having that information allows us to be more proactive and, you know, inform our customers that, you know, we might be able to get their product or we won't, there'll be challenges, that kind of thing. So at this point in time, you can see on this graph, on the previous one there, we were all asking questions, you know, remember the mill manager coming to me at the time and saying, can you have a look into what's going on? Why aren't we getting our glulam products, for example? And then by the time we got to here, you know, we're going on a couple of years of this lower AWV log coming through. And that point, we're all already well and truly into it. And we had to, at that point, we started making decisions around our glulam product and actually had to do some product development to come up with other glulam beams that we could supply in the volumes that the customers wanted. So that was the development of our Beam 15 product. It'd be nice to know that back here. We could use that Resi data to give us much more detailed information, remembering too that we've got looking at average AWV here, whereas the Resi would give us more detail of what's happening throughout the log so we could cut better. So at the moment, this is where we're sitting. So we're starting to go back up again, but it'd be nice to know what's going to happen in the next 5 to 10 years. You know, do we need to look at changing again? Can we supply a previous product that we took off the market? There's a lot of questions there that we could, if we had those, all the Resi information, would inform those questions. So this is going back to the question that I mentioned has been going around Hind for a little while, for the last few years, is when is a tree ripe? So currently with the age and geometry, it just doesn't tell us all. We do get more information than that, but if we can get detailed information of the MOE or density across the cross-section of the logs, then yeah, we make very different decisions. So we can get a log that looks similar. We can get a log that has an average AWV that is similar to each other, but this profile looks very different and we would cut it very different. We'd be able to optimize it very different. So there's a whole lot going on there. We've got different customers that want different things. So I don't know if anyone else has heard of baked green bananas, but I certainly hadn't before I did my Google search. You can see, like, you know, our glulam customer is going to want a different tree to be able to capture the product they need, whereas our general customers that want things like frame and truss, you know, we need to target, make sure we can get enough of what they need. And then we've got for example, our industrial products. So our sleepers and that sort of thing, we would cut, for example, this log for those products. So having that information allows us to go, well, we won't even try to get any framing product out of that. We'll just put it all into industrial product. Whereas this one, we'll put a different sawing pattern over and get majority of a framing product out of it. So short and sweet, but that's it.
Thank you very much, Rebecca. That was great. And it was actually interesting to see, you know, how you'd picked up that variation in MLE and how it'd gone down and on the way back up.
Yeah. I think there's a lot of further potential for research to link other things as well. So that's, you know, I know that's further down the track, but I think it's pretty exciting.
Have we got any other questions for Rebecca there?
Yeah, just a quick question. Rebecca, what does the AWV stand for?
Average wave velocity.
Average average weighted velocity.
Wave, wave, average wave velocity. So your acoustic.
Oh, okay.
measurement. Yep.
It's a environment. Okay, thank you.
Hi, Rebecca. Chandon here from DAF.
Hi, Shannon.
How are you? Just a quick question. How flexible or difficult it is to change the sowing pattern in your mill? Can we change it for every tree or every plot? Or how does it work?
Sorry, how difficult is it
to change the sowing patterns?
The sawing patterns. So
yeah.
It depends. It doesn't change on the fly. So we have a set pattern in the center of the log. We can change our sideboards a bit, change around. Our Tumbarumba mill's much more flexible, but at Chuan we've got them fairly set. We don't have a lot of variation that we can do on the fly. But there's potential to sort differently, sort by sawing patterns, sort by, there's a whole heap of things that we could do. Which again is another research and optimization opportunity, I think.
Yeah.
To come up with some more ideas on how we can make that efficient.
Anybody else with any questions?
Yeah, Dave, I've got a general question to everyone, and particularly Jeff. One of the problems that we have we are having a look at hardwoods for veneer or for plywood, and obviously big problem is splitting. And I know splitting is internal growth stresses. And I'm just wondering, has anyone had any success with any form of prediction of splitting or propensity to split using Resi?
No, not that I'm aware of. Yes, splitting is something that's probably going to be more related to microfibril / chemistry localized problems, which I'm not sure that Resi is going to give you that sort of information. I don't know whether, John, if you want to comment at all, whether you've looked at splitting, but a lot of work's been done on splitting here in nitens and globulus, and it's hard to predict.
Yeah, it's definitely worth a look, because some of the stuff that Bilius has been seeing mechanically around the way the needle wears and the fiber interaction, that growth stress will be seen by the needle one way or the other. The really interesting piece will be trying to find some reference against which to assess the change due to growth stress. But it's definitely worth a look.
So one of the things we haven't really looked at yet, and we're just starting to turn our mind to, is using forward resistance as well. And forward resistance in combination with turning or drilling resistance. And yeah, maybe looking at it in that way might be of interest.
Yes, so we tried a little bit to work on checking for eucalyptus nitens. Yeah, and yeah, it was possible. Like not strongly, but a little bit, like to predict the checking. So for the Resi amplitude, it showed that there is a I think moderate relationship. So yeah, it's going to be published, this paper, soon.
Excellent, thank you. That will be great.
And Charlie, that splitting, is that related a lot to tension wood stuff at all, or
No, not really. No, it's not tension wood. And it is under strong genetic control, because a number of companies have bred it out of Eucalyptus grandis, and they've got low splitting populations. What is causing it? I'm aware it's movement of moisture and internal growth stresses, but beyond that, I don't know.
So you might call it a eucalypt venereal disease.
You could well do, Jeff. That would be the Australian view.
getting the talk back on track, is there any more questions for Rebecca? No?
Just a comment, I guess, that Rebecca's talk really highlighted, as Rebecca said, the value of the sort of work that Brian's doing there in terms of being able to predict forward and then monitor and manage wood quality going forward as a forest grower. And in southern pine, where density is not such a great predictor, very keen to extend that functionality through to MOE in the future. But yeah, there's just so much potential there for adding value at the mill by what we send them and when. Thanks.
Yep. Well, I really appreciated your talk, Rebecca. It was actually great to see, from a processes point of view, because as a group, we've been working with the Resi, mainly from the growing side, and see how you perceive, the potential benefits and if we'd be able to warn you about those sort of drop-offs in wood quality, might have been made Hein's job much easier. I guess the thing with this, we have to start wrapping it up. I'm just going to share my screen. Hopefully you can just see the thing. Would really encourage people to actually get in contact with either myself or Jeff to nominate to give talk in something like 4 to 6 months' time. Probably we're talking about October, November type period, where we'll try and run another of these Resi Users Group webinars. And I guess the one thing with this is that, initially this whole thing was started from an Australian context, but we're actually working with UFRO, try and make this something where we're bringing technology and understanding about how people are using the Resi and an international scale. I'd like to thank everybody for attending and really thank the presenters, Brian, Billis and Rebecca, for their great talks today. And, look forward to seeing you all in, like I said, 4 to 6 months when we'll have hopefully the next of these meetings. So thank you, everybody.
Thanks, Dave, for putting it together. Certainly we'll consider a contribution at your next meeting. Thanks a lot.
Okay, Charlie, that'd be great. Thank you.
Thank you, Dave.
Thanks, Shopping.
Thanks, everyone.
Thank you.
Oh, thank you.
Thanks, everyone.